Okay, our second example involves a helicopter, and we're going to talk about two important components, the vertical and horizontal components. So examining a scenario that's happening and saying, okay, how much, how do you resolve the red vector into two components, but instead of along two ropes, we're going to go along a vertical component and a horizontal component. And we're going to talk about a helicopter taking off. And I'm sure we've all watched TV and seen a helicopter taking off, or maybe we've actually seen it in real life. But you'll notice I've got my helicopter picture here. And again, as always, try not to get distracted by my brilliant artwork. But helicopters, when they take off, they don't just sit there and go straight up and then forward, right? They usually go up and an angle at the same time. And in fact, their nose kind of is tilted a bit. And you'll see that when they take off, they sort of go up and they go like this, going both forward and vertical at the same time. So in our example, you'll see that it's going up with 3,200 newtons of force up at an angle of 5 degrees to the vertical. So it's going off something like this. And we can really get a good view of our helicopter taking off if we watch this. Okay, now I'm just having fun. So anyway, our helicopter is taking off at this little path here. We'd like to know what its vertical and horizontal components are. The vertical component is something we call the lift, and of course the horizontal is how fast it's going forward. So now we're going to draw the two vectors that are here. There's two ways we could draw this, but since the vectors can be added in any order, I'm going to actually draw the forward vector first, which goes to about here, and then the horizontal, or the vertical vector there. I could have drawn the vertical vector here and then added the horizontal. It wouldn't matter. You get the same picture and the same answer. But I'll stick with these two. I'll label them as my vertical lift vector and my H horizontal or forward vector. The nice part about these two components is that you get a right triangle. So since we got a right triangle, we probably don't need to use the sine law and cosine law. We can just use SOHCAHTOA. But again, we need some of the angles inside that triangle. Since this is 5 degrees and we have a right triangle, this is going to be 85 degrees. And we know that the red vector is 3,200. That's our hypotenuse. So now to find the vertical one, we just got to figure out from SOHCAHTOA what's our information. Well, we're going to use the 85-degree vector, which makes this the opposite, and our known is the hypotenuse. So we're going to use sine. So sine of 85 is equal to V, opposite, over hypotenuse, 3,200. Very quickly, the math would tell me that I'll multiply by 3,200, sine 85, punch that into my calculator, and I get an answer of 3,187.8 newtons. We can do the same thing with H, except if we use 85, H is the adjacent. We'll still use 3,200, but this time we'll use cos. And so it'll be cos of 85 equals the horizontal component over 3,200. Isolate for H, divided by 3,200 means we multiply. So 3,200 cos 85. Punch that in our calculator and we get 278.9 newtons. If we look at our question, of course, this makes sense. It is lifting more than it's going forward. It's only 5 degrees, so majority of the 3200 is the vertical component and a little bit of the horizontal component. And if this helicopter, was angled a little steeper like this, we'd have probably more vertical or more horizontal than vertical. But get it back to where it belongs. The nice part about finding horizontal and vertical components is that they are 90 degrees to each other. We have a name for that. They're called orthogonal components. Remember that word orthogonal? It'll come up for the next couple of units. Orthogonal components are components that are right angles to each other.